Hello and welcome to chapter 27 on the topic of color. Okay, so we're going to be talking more about light, but specifically, where do colors come from? A lot of interesting ideas in this chapter. Should be very fun. Okay, so we have the topic of colors in our world, right? How do we make sense of what we see? Then we'll talk about selective reflection. This will be a big one to explain why certain things are certain colors. Selective transmission, which is, we've talked a bit about transmission already, so it'll be kind of as well as a review. We're going to be talking about mixing colors, pigments, and then a couple of interesting explanations. Why is the sky blue, and why are sunsets red, and why are clouds white? All right. Oh, and why is water greenish blue? Okay. All right. So, color. First of all, we should acknowledge it is a physiological experience. It's in the eye of the beholder. People do experience colors differently. They can have different processes going on in their brain, in the cortex. They can have different preponderances of cells in the fovea of the eye in terms of the specialized cells for seeing red, green, and blue. So absolutely, they're not all the same, but there is kind of a general human average about how we see color. But there are definitely exceptions. Okay? All right, so color we see depends on the frequency of light. We definitely know that color and frequency are one and the same. When we think about the visible light spectrum, or the small amount of the entire electromagnetic spectrum, which is visible light, it is definitely composed of those colors separated by frequencies. All right. The lowest frequencies are perceived as red. All right. That's going to be around 500 nanometers in length. Those are the longest waves that are visible to the human eye. And since they're the longest wave, that 500 being the longest you can see at the human eye, it is the lowest frequency. Because as wavelength goes up, frequency goes down. And that's based on the relationship that the speed of light is equal to the wavelength times the frequency. Okay? And so the speed of light is a constant. If you change the frequency, you must also change the wavelength. Okay? So in between the lowest and highest frequencies, perceived as the colors of the rainbow: red, orange, yellow, green, blue, indigo, and violet. All right? And then we have the highest frequency, which is perceived as violet. That one is going to be around 280 nanometers. All right? So that's the entire spectrum, light between the length of 500 nanometers and 280 nanometers. Now, see how we're kind of simultaneously talking about frequency and wavelength? That's because they're one and the same. When we usually talk about the light, it's usually easier to talk about the values of nanometers because they're nice numbers that are easy to understand: 280, 500. The frequencies are so high, they're in the gigahertz range, that the numbers don't make as much intuitive sense. So you're going to see wavelength referred to more frequently when you see light. If you look at a laser, for example, the laser will be listed as its wavelength rather than its frequency. But you can easily convert one from the other. You just have to divide by the speed of light, which is 3 times 10 to the 8 meters per second. Okay? And then there's light that's invisible. Obviously, there's lots of types of light within the broad concept of light, the electromagnetic spectrum, which is invisible, including radio waves and X-rays. But just outside of visible light, we have ultraviolet and infrared. Okay? Those are both invisible. Okay? All right? Which is the question here, right? Which ones do we not see? Both of these, infrared and ultraviolet. These are lights that are invisible to the human eye. Okay. Now, some animals certainly, right? Some organisms can see these types of light because they do pass through the atmosphere. There is ambient infrared and ultraviolet light in the world that we live in. Absolutely, lots of it. It kind of depends on the kind of the phylum of organisms and whether it was probably an ecological stress, a survival of the fittest in terms of the evolution of the species to see those types of colors, because by far the strongest wavelengths that pass through our atmosphere are the visible spectrum to humans. So it definitely makes sense that a lot of animals like us see the same colors. Okay. As far as seeing ultraviolet, that light is definitely around. It's somewhat harmful, so sometimes it kind of makes sense that a complex eye would not see ultraviolet because that's potentially high energy photons that could damage cells. So why would a cell to evolve to even see that type of light? To be able to handle such a high energy input, it's probably better to just not have that mutation, not even bother with seeing that type of high energy light. Just avoid it altogether. But there certainly are cases where probably there is byproduct of other types of light, or maybe simpler eyes, the eyes of insects, for example, that can see that ultraviolet light. There's other cases where seeing ultraviolet light is very important. When we talk about very briefly at the very end of this lecture, we talk about the ocean. The ocean absorbs red light, so the blue light's passing through, including the light that's even bluer than blue, ultraviolet. And that means that for marine organisms, especially deeper marine organisms, it absolutely makes sense to see that light because it's some of the only ambient light that's around, until eventually there's almost no ambient light and it's just a world of darkness if you go deep enough in the ocean. Infrared is interesting because you think one thing where infrared is going to show up in the near infrared, that's light that's passing through the atmosphere. There's also that's kind of near in the sense of near to the visible range of the electromagnetic spectrum. But there's also what's called far infrared, and the idea there is that's the type of infrared that your remote control uses. Well, that's somewhere in between, but it uses that invisible light. Lots of sensors, like on the conveyor belt at a checkout stand at a grocery store, would use that, the kind of infrared which is bordering on far infrared. But I guess the best example of far infrared is the heat signatures from sort of room temperature objects. So, objects that are at temperatures of around 390 Kelvin or 20 degrees Celsius. Well, the molecules are vibrating, they're emitting light, low energy light, and that's in the far infrared. So seeing infrared is like heat vision. Well, can some animals, see heat? Yeah, they've actually developed the ability to see the infrared, to actually see the heat signature. It's definitely rare in mammals. One of the cases that I've heard of is biologists have been able to show that reindeer have actually had that ability and have evolved to see the infrared so they can pick up white predators on a white background. But it's such a rare mutation in mammals that it makes sense that it would take an incredibly strong selection pressure in order for it to actually be selected for, through sexual selection and actually have, or just survival, and then actually have that that ability to see infrared. Okay, all right, so cool stuff. All right, so that's kind of the colors we see. Now, why do we see certain colors? Or why do things appear certain colors? One of the biggest reasons is selective reflection. Okay, so the rose, we'll kind of come back to this example. Roses are red, right? Obviously, there are many colors, but we'll consider a red rose. So we would see the color of the rose by the light it reflects, right? So if I look at a red rose, that's because it is reflecting red light and absorbing other frequencies of light, other wavelengths of light. So in a sense, the color that you see for an object like the red rose is the one color that object rejected. It absorbed all the other colors, okay? And that's the color that it appears to your eye, okay? Because that rose is, in most conditions, being subjected to white light because we assume sunlight, okay? So we're assuming sunlight. Now, do we always live in white light environments? No, we create lots of artificial light and live in artificial light environments. But usually artificial light is at least, if not perfect white light, at least a good approximation of white light. Now, there are exceptions, okay? Furthermore, there are some things that don't produce light just through selective reflection or don't appear color, and those are things that are actually emitting light. So a glowing object, like a glowing gas discharge tube, that's actually an atomic emission. You think of an LED, that's actually producing the light, so it's emitting light. It's not selective reflection, but those are things that are glowing. So unless something is actually glowing, or maybe it's glowing so hot that it's actually glowing in thermal radiation, but approaching the visible spectrum. But with those exceptions of glowing objects, everything that we see, every color we see, is selective reflection, where the actual original source of energy was either the sun or some other white light source. Okay? All right. But what if the source isn't white light? Well, you can definitely set up experiments. You can create lights that aren't white light. You can have red lights and green lights and black lights, which are actually ultraviolet, and also violet and ultraviolet, your typical black, quote unquote black light. And in that case, you can have these interesting effects, right? So okay, so let's read this slide real fast. So objects reflect light of some frequencies and absorb the rest. Okay, so rose petals absorb most of the light and reflect red. So that's the one type of light they reject. Objects that absorb light and reflect none appear black. Okay, so if you look around, if you see a black object, that object is absorbing all the colors of the visible spectrum. And so that's why it doesn't appear to have a color. That also means that it's going to be taking more of that light energy in, and that light energy has to go somewhere. That's why black objects heat up faster in the sun, because that energy is becoming the random motion of the particles in that object, which then means it becomes warmer to the touch. Okay? But then look at this. Objects can reflect only those frequencies that are present in the illuminating light. So again, if we assume white light, then yeah, we have a true picture of the color, right? Quote unquote true, right? But again, if we were at a different planet around a different star, then there would be different light, okay? But again, we have our light of our sun. It's the light we're used to. We call it white light, okay? Now, But, so this is the red ball in white light. What if you put the red ball in red light? Well, in that case, it just appears extra red, kind of like a really washed out red color, because it's basically reflecting all of the ambient light. So it almost appears to glow. It's like it appears to be much brighter compared to its background, because again, it's reflecting all of the ambient light. On the other hand, if you put it in a room where you have a green light bulb, the only source of ambient light is green, then now your red ball actually appears black. Right, and that's really a striking example, right? Because it really looks black, but it's still a quote unquote red ball, right? Or it just rejects red light. It was never actually red, right? It just rejected red light. And we can really see then the subjectivity of saying that it's red when we see it as black in a green illuminated room. Okay? As far as selective transmission, you can have stained glass or colored glass, in this case blue glass. The idea there of blue glass is it only emits blue light. Now we already talked about glass in the last chapter, because glass is very interesting because it already rejects or is opaque, which is non-transparent, to UV and or infrared, all right, IR. And so it was already rejecting those two wavelengths, any glass, even glass that isn't colored. And so glass always will heat up because the ultraviolet and the infrared light is going to the glass, getting stuck inside the glass, turning into thermal energy. But if you take blue glass, which only allows blue light to go through, that type of colored glass will actually heat up even faster than normal glass, because it's got all these other colors which are then just being turned into heat energy. Okay, all the radiative electromagnetic energy is just turning into heat energy, turning into the random kinetic energy of the particles inside the glass. Okay. So as far as mixing colors together, we're going to talk about this quite a bit over the next few slides. But first of all, let's acknowledge that not all colors are created equal. So the distribution of solar frequencies is uneven. So the light that comes to us, this composite light that appears white, because it's the colors of what we call the rainbow, everything from red to violet, well, it's definitely not equal intensity. The brightness of the light, both in terms of what's actually created on the surface of the sun, and then furthermore what's selected for and is able to pass through the atmosphere, is not all equal. In fact, the peak is right at basically yellow-green. And that yellow-green peak is directly related to the surface temperature of the sun, which is 5,600 Kelvin, because that's actually then the peak frequency of the sun. And I always like to point that out because that actually means that we have a yellow-green sun. We really do. Our sun is yellow-green. That's the peak frequency. That is the most common photon that is created from the surface of the sun. Photons are particles of light. We'll talk about those more later. Okay, but that is definitely the most common type of light that's produced. But it's not the only type. There's a good probability of other colors being produced on the surface of the sun, but with less chance, thus less brightness or less intensity. Okay? All right, so there we have it. Most common light. Now that actually has a direct consequence too to the fact that we've evolved to see that light, because the human eye, much like very many of complex surface dwelling eyes of organisms, is fine-tuned to that yellow-green color. So that's the color that we can see the best. Green, like if you take two sources, like I think the best comparison is lasers here, because we can directly then compare wattages. So you consider like two 200 milliwatt lasers, so equal power lasers, and one is red and the other is green. The one that's going to appear brighter is the green one. It's also the one that can actually more easily damage the eye, because the eye is more sensitive to the color that is around more. All right, we've evolved to see it. Okay, so. And considering the radiation curve, we can divide it into three regions. This is the overall radiation curve of the light that's created by the surface of the sun that match the color receptors in our eyes. Okay? Red, green, and blue. So we often talk about these as being the primary colors. And again, that's because we have particular cells in our eyes that pick up red, green, and blue. So these are important colors for us. Okay? And these are known as the additive primary colors. Okay? So this is kind of a key term here. Additive primary colors. And it's additive because if you take red, green, and blue, then you can create any color in the spectrum by adding them together, right? Consider some sources of light, red, yellow, and green here, and shining them together, you can create any color you want by overlapping them, so essentially adding one color on top of the other. What happens if you put them all together? If you take red, green, and blue light and you overlap all three, you saw on the last slide, that's white light, okay? So white light is the sum of the three primary colors, red, green, and blue, the additive colors, okay? And it's definitely an idea of of having overlapping light sources and is totally consistent with the light that's coming from the sun, the overall spectrum of visible light from the sun. Okay? All right, so when the color yellow is seen on your TV screen, the phosphors being activated on the screen are, right? So how do you make yellow? By adding colors together, because it wasn't one of the primary ones. So what do you add together to get yellow? Red and green. Okay, red and green make yellow in terms of the additive colors. Okay, makes sense. So a blue object will appear black when illuminated with, this is, think back to the slide that had the ball illuminated by different colors. All right, in that case, it was a red object that appeared black. All right, but here's a blue object. So which of these options has no blue in it? Okay, yellow, right? Because yellow is completely separate from blue. It's a totally separate part of the visible spectrum. And so if you illuminate something with pure yellow light that has a natural ability to reject blue light, and thus appear blue when it's exposed to full white light, full sunlight, well, it would appear black because now it has no light to reflect. Okay? All right? So because it just absorbs the yellow. Now, different type of light. Subtractive, well, no, I'm sorry. Not different type of light, different type of color. All right? Subtractive primary colors. Okay? You probably heard of these as well. They get talked about less in elementary school, but you still have probably heard of them. And those are magenta, yellow, and cyan. And you know where you probably heard about them? Printers, of course, right? And the idea is that they come from adding together two of the additive colors. So magenta is red and blue, yellow is red and green, and cyan is blue and green. Okay? So each of them is a combination of two of the three additive primary colors. Okay, so far, that's what they are. So we got their names, and we know they're called the subtractive primary colors. In a minute, we'll talk about why that name makes sense, but for now, let's just consider what they are. All right, so here we have how you could kind of create them. So the shadows of the golf ball are subtractive. Let's zoom in what's going on here. So essentially, you got blue light coming from this direction, green light coming from this direction, and red light coming from that direction, right? Looks a little orangish on my slide, but it should be red. All right, and so then what happens is that in this shadow, for example, this one here, well, there's no red light because it's being completely stopped, but there is still going to be green light and blue light. And so the effect is, right? Well, the effect is cyan. So this one right here is cyan, okay? Looks, again, sort of bluish, again, because of the limitations of the slide, okay? All right. And then we've got the magenta one, which is the shadow behind green, because it's just the combination, because none of the green light is making it there. So only two light sources that are making it are the blue and the reds, making cyan. All right. And then finally, you've got the yellow, right? Because the yellow is then being created by the green and the red, but not the blue. Okay. So that's the yellow right there. All right. So that's a good way of thinking about how you could make the subtractive colors in the shadow of something, of an object. Okay. All right, by orienting three light sources of the primary additive colors. All right, now the subtractive primaries are complementary to the additive primaries. So if you take magenta and green, you get white, because now you have all, excuse me, you have all the colors together, because magenta, after all, is red and blue. So effectively adding magenta and green is the same as adding red, green, and blue, which of course gives you white. If you take yellow and blue, all right, then you get white, okay? Well, you get white plus red plus green plus blue, all right? Okay? All right, so you see how you're bringing those colors together, and the example of that is color printing, okay? And this one, I see there is a typo here. There should be a equal sign, not a plus, because you get white, because yellow and blue gives you white, because yellow is red and green, okay? So this, I'll underline just this. Yellow is red and green, and then when you add blue to red and green, you have all the colors, all the primary colors, so you get white. So again, this plus sign should be an equal sign. That is a typo. Okay? You guys see what I've written over it, made it the equal sign that it should have been. All right, so hopefully that's clear. All right. Oh, there. Okay. All right, so a red rose will not appear red when illuminated only with, okay? So think about this. What color would make it so we don't, we don't see red, okay? So we need a light source that doesn't have any red in it. Which of these? Well, obviously not red. Orange has red in it. White obviously has red in it. So cyan, because cyan is blue plus green. So illuminating a red, quote unquote red, again, what is red? It's just the color it rejects if that color is around, right? So if you illuminate it with blue and green, which is cyan, there's no red in that light, so there's nothing for that object to reject that would make it look red. So it's just going to absorb all of the ambient colors, the cyan light, so it just appear black. Okay? All right, so it's as far as mixing color pigments and this idea of using the subtractive colors for printing, it works really well. So only 3 colors of ink are used to print color photographs: magenta, yellow, and cyan. So magenta, yellow, and cyan. And that creates a full color image. And then we add black in order to create the finished result. Now you might be like, wait, why do you need black? That seems, I thought you could make everything with just magenta, yellow, and cyan. Why do you need black? Well, you actually don't need black. Often printers will have a separate black cartridge for just kind of efficiency and saving money, because the only other way you could make black, because you can, but you would have to add together all 3 of the subtractive colors. You'd have to add the magenta, the yellow, and the cyan together, and then you can make black. And in fact, you've probably seen the printer ask a printer, if you've used one right at home, ask you that. Well, do you want to combine all your colors together to create black, since your black has run out? And you can choose that, and it will work just fine, because you absolutely can create black. But then you're using your color cartridges or toner cartridges to create the black. Okay. So the subtractive primary colors are cyan, yellow, and magenta. Okay, if you haven't noticed. When white light passes through overlapping sheets of these colors, lights of all the frequencies is blocked. It's subtracted, and we have black. So here is really why the name makes sense. Because if you overlap the subtractive colors, the effect is black. All right. So here's the idea, right? You take like a sheet, like a transparent sheet of cyan, magenta, and yellow, and where all 3 of them overlap, you have a black rectangle. Okay, so that's really how the name makes sense in terms of the light that's actually passing through. All right, so where only cyan and yellow overlap, the light of all frequencies except green is subtracted, and various properties of cyan, yellow, magenta dyes will produce nearly any color in the spectrum. Okay, so that's the subtractive colors as compared to the additive colors. All right, okay, so now we'll move on to the last topics of the chapter, and a couple fun ones. Why is the sky blue? Why are sunsets red? And why is the ocean greenish blue? Okay, so the sky is blue because of scattering. Okay, so the idea here is that in general, smaller particles scatter a shorter wavelength light. So smaller particle scatters shorter wavelength light. And what's the shortest wavelength light? Blue. Okay, and so since the atmosphere is primarily going to be composed under most conditions of very small particles, and that's of course on our planet, different atmospheres will be different, but on our particular planet, the typical atmosphere is composed of very small particles relative to the light that our sun produces. Right? Again, it's it's very planet specific, but then that means that the light then that is scattered matches those small particles, and it's the shortest light, and it's the blue light. Okay, so the blue light gets scattered. All right. It gets scattered in many directions, it's true, but there is actually a most common direction, which I'll mention in a second. Okay, so to sum it up, it's due to selective scattering. The blue scatter light predominates our vision because it's basically filling our vision. It's a light that's kind of bouncing off in every direction, so it appears to be the light when we look up towards the sky, because that's the light that is being kind of ricocheting around, for not a technical term, but kind of a cartoonish visualization of what's happening. So it does vary in different locations under various conditions. So if you have a clear, dry day, that's a deep blue. When there's water molecules, so you have some humidity in the atmosphere, that creates a beautiful blue. All right. When there's lots of dust particles, then things can actually appear more white. You have a whiter sky. And after heavy rainstorms, when a lot of the airborne particles have gotten washed away and only the smallest ones remain, that's going to be the deeper blue again. All right. So you can see the deeper blue occurs when it's just the smallest particles are in the atmosphere, under whatever conditions has created that. Okay. So that's the blue sky. Okay. Okay. So a white sky is evidence that the atmosphere contains what? Because we see lots of times when the sky is white, cloudy day. Okay. All right, and it could be very high clouds even, but still you can definitely see that the white appearance in the sky sometimes. What would make it white? Think about what we were talking about. If very small particles only scatter the shortest wavelength of light, and that makes it blue. So then if you had really large particles, if you only had large particles in the atmosphere, then you would have a red sky. We'll talk about that in just a second. But If it's white, then it's got to be a mix, right? So it's basically all sizes of particles, because you have a basically overlapping scattering, and the effect that the eye perceives is those colors overlapping, which is white light. Okay, so it's scattering happening at different frequencies, different wavelengths, both the low and the high end of the visible spectrum. Okay, so then what about red sunsets? So light that is least scattered is light of low frequencies, which best travels through the air. Okay, and that's going to be the red, the orange, and the yellow light. Okay, because that light didn't get scattered; it actually passed through. Okay, so and that also does have the implication that there is slightly less blue light that even makes it to the surface. Even at noon, right? Because some of that light got scattered in the atmosphere due to all those particles making the sky blue, and so that means that basically, objects that are blue in color, that have the ability to reject blue light and appear blue, they're always going to be less bright because there's just less blue light making it to the surface. And you think about it, there's actually a lot of less. There's less things that are just naturally blue. It is one of the kind of the rarer rarer colors in terms of pigments and just like things that reject that blue. And you got to think, in terms of like biology, it kind of makes sense because it's going to be the color that is just that's around the least. And even go back to the spectrum of the sun, right? It's the weakest light that's even produced at the surface of the sun. So it's doubly weak. There's less light that's in the blue coming from the surface, and then some of that light gets lost, some of its intensity gets lost due to scattering in the atmosphere. But still, blue light does make it to the surface. But when it really doesn't make it to the surface is during sunset. Because at sunset, there's been so much scattering, such a long path of the light passing through the atmosphere, that when you look in the direction of the sun, you're basically just going to see the red light that's making it, okay? Because it went through because once the angle becomes very steep, what was a 100-kilometer thick atmosphere at this point can become 10 times thicker, and that makes a very big difference on the actual color that reaches you. That's why sunsets are red, because of all the scattering that happened between the sunlight entering the atmosphere and then the sunlight reaching your eye, okay? All right, so that's the red sunset. Furthermore, because you think about it, okay, well, is there, like I mentioned, that there's a directionality, and I'd come back to it, and that's because what's happening is that because the sunlight is predominantly coming in at an angle, and then this basically the blue light is then getting reflected straight down. Basically, usually the most common reflection angle is going to be 90 degrees, and that's due to the wave-like properties of the light as well as their particle-like properties. And due to that angle of 90 degrees being most common, then there is this greater likelihood of the light getting scattered basically perpendicular. So the scattering angle of the blue light is mostly going to be in this direction, not entirely, but mostly in that direction, which is all the more reason why the light that reaches you at sunset is red. Okay, so that directionality does have a role to play. All right, so a variety of sunset colors is evidence of a variety of, right? Well, atmospheric particles. You're going to have all different types of sunsets, right? Sometimes they're a pinkish color, sometimes they're a red color, and that's because of the different combinations of colors that were absorbed along the way for that light to reach you through the very thick atmosphere it had to pass through. So if molecules in the sky scattered orange light instead of blue light, sunsets would be, well, they'd be blue. All right. So this is where I'm going to come back to the idea of a red sky, because we recently had it happen here in the Bay Area. We had a very, very noticeable red sky after a series of fires. And what was causing that was large particles in the upper atmosphere. And so what was happening is that there was really no opportunity for the low wavelength, the short wavelength, high frequency blue light to get scattered. Instead, only the long wavelength red light, right, was getting scattered. And when that long wavelength got scattered, then we were seeing a red sky, okay? And that red, it was so pronounced because it really looked red. It looked like we were on Mars, because Mars is known for its red sky, right? Just only basically no small particles in the atmosphere, just a huge amount of large particles dominating the atmosphere, okay? And so that begged the question, on those days where we had a red sky, did we have blue sunsets? I don't think we did. Now, that's not to say that's impossible that we did. And that's probably due to the fact that those particles were in the upper atmosphere. And so what was happening is the effect of the sunset. So the large particles were only up here in the upper atmosphere. And so then the actual effect of the sunset wasn't really making the sunset blue, because it wasn't actually scattering only the red particles on the path. There's still an opportunity for the red light to get scattered as well. So blue light would have been, or rather, there was still an opportunity for the blue light to get scattered as well as the red light. So the sunset was probably just drab, okay? it was a really basically an uncolored sunset, despite the red sky. Now, that's not to say it couldn't happen. You could have a case where you have a lot of large particles in the atmosphere, so much so that you could have an eerie blue sunset. Because basically in that case, the blue light is allowed to pass through because all those big particles are probably like clumped together with what would have been the small particles. There's really no opportunity for blue scattering. So you're effectively it's like a filter allowing the blue light to get through, and you would truly have a blue sunset, right? Which would be quite a strange sight to see, all right? And it's probably happened. I haven't been able to see documentation of it. Okay, so as far as clouds, well, clouds are white, and they're white for kind of the same reason we're talking about, because it's an overlapping of lots of scattering, okay? So the idea is that in your clouds, you got tiny clusters produce bluish colors, so the tight, very small pockets of water molecules combine. But clouds are never just water; they always have some dust in them. Otherwise, actually, the water molecules wouldn't be able to stick together. They have to lose some energy by bouncing into dust particles. Slightly larger clusters produce greenish colors. Large clusters produce reddish colors, and then the overall result are the white clouds. All right, and slightly larger clusters produce a deep gray, because at that point you go from white to just so much light getting absorbed that you start to lose the light, and then that's where clouds become dark. And once they become dark, then you know that they become so dense, so opaque to light passing through, that they're probably going to start dropping raindrops. Now, what about water, right? Because is water blue because it just reflects the color of the sky? Absolutely not. The reason for water being the color that it is, a greenish blue, is a different phenomenon, kind of similar to the idea of the small particles in the upper atmosphere vibrating around at the low frequency that matches blue light. So kind of a similar idea, but not because of the sky, just because of similar physics. All right. So water molecules resonate somewhat in the visible red. Okay. So that's the idea. Is the molecules, the H2O, they actually have a resonant frequency. They're able to vibrate easily at a wavelength that matches visible red. They have other resonant frequencies, including microwave frequencies of about 2 centimeters, but they also have a less intense resonant frequency around visible red, around that 500 nanometers. Okay, and so they vibrate easily, basically turning the electromagnetic energy into heat energy, and that means that the light is gone effectively. That light has changed from one energy form to another. Okay, and so it causes the red light to be a little more strongly absorbed in the water than the blue light. So then red light is reduced to 1/4 of its initial brightness by 15 meters, just kind of case in point that red light is effectively disappearing or turning into another form of energy. And there is very little red light in the sunlight that penetrates below 30 meters. At that point, it's only the blue light that's going to penetrate more deeply. All right? So when the red is removed, what's left over? All right? Well, if you take away red from white light and consider additive colors from earlier in the lecture, then you're going to be left with cyan, a bluish green color. So water is cyan, because it's the light that wasn't turned into the random kinetic motion of the water molecules. All right, so that's the actual light that we see that's left over as electromagnetic energy is the bluish green color. Thus water appears bluish green. All right, and then but just like the sky can vary, so can water. You can add in other particles and change the color of water. So the intriguingly vivid blue, if you've seen pictures of this vivid blue color in the Canadian Rockies, is due to scattering, and it's due to because of particularly fine particles of silt that exist called rock flour, that exists in the water, changing the color of the water, basically changing the types of colors that it can absorb and the types of colors it can scatter. Okay? All right, and obviously you can dye water by putting in other particles as well. All right, so that's it for our lecture on color. I hope it has been interesting and informative.